Here we are in chapter 3, where we're going to start looking at the architecture and organization of a computer. And we've talked a little bit about this instruction set architecture in our previous chapters. And so here is where we're really going to dig into that into more detail. So let's talk about what we're going to learn in this section. So what we're going to do is talk about that ISA, that instruction set architecture that describes the assembly language programmer's view of a computer, stresses its functionality rather than its internal organization or implementation. And we've talked before about how the ISA tells us what the machine does, whereas the organization tells us how it works. So in later chapters, we'll talk a little bit more about processor organization and explain how a given ISA might be implemented. But for right now, we're going to look at how we can store our program machine, how instructions are executed, look at instruction formats, demonstrate how a processor implements conditional behavior by selecting our alternative actions. So kind of building on what we learned in chapter 2, where we talked about that logic. And then talking about how the computer instructions show how computers access data, those addressing modes that we've maybe touched on just a little bit. And then we're going to talk more about ARM, ARM's development, how ARM programs are written, and how ARM uses conditional execution. And so remember at the beginning, I talked about how, there's a different architectural platforms when it comes to microprocessors, but that we were going to focus specifically on ARM. And so that is what we're going to be really talking about when we dig into this instruction set architecture. So let's talk about how the CPU reads instructions from memory and executes them. So a microprocessor, like the ARM, has this stored program architecture that locates programs and data in the same memory and operates in what we call the fetch execute mode. So in this mode, instructions are read from memory, decoded, and executed sequentially. So in an ARM system, the computer has these registers, right? We've learned all about the registers at this point. We have an arithmetic and logical unit, usually abbreviated to the ALU, memory and buses that link these components. And so we're going to look at how a program is loaded into memory in the first place. So it's either always there, stored in the type of read-only memory that we'll talk about a lot later, or it's loaded from disk by the operating system. And our registers that we've talked about before are the storage elements located within the CPU that behave just like storage elements in memory. And some CPUs, such as those found in like embedded applications, have no more than 20 registers, which, it's not a lot. Other computers can have well over 100, right? And that's really how we get our more like sophisticated and modern computers, because we need all of these registers, all of these different places to load in all of the different applications and things that we're trying to do. And looking at the figure, and we've looked at this before, our registers have names, usually starting with R0. ARM has different register names. They're AX, BX, CX, DX, etc. Intel uses a D system, so D0, D1, right? And so every architecture is a little bit different in how the registers are named, but essentially they all work the same. Now you might be kind of asking yourself, like, why do we name our registers like this instead of using addresses like we see in memory? And really it comes down to our computer instruction using relatively few bits when we want to reference a register. So the register select field of an instruction might only be 3 or 5 bits, depending on how many programmer visible registers there actually are that you're allowed to use. And we use a different addressing set for our main memory because we have a much greater storage capacity, right? We're looking at, 16 gig, 32 gigabytes of memory. At least right now, some computers even have more. And these memory areas are referenced by an address that might be 32 or 64 bits long, right? So a computer with 32 general purpose registers might require only 5 bits in the instruction to specify a register, where if it takes 32 bits to uniquely access one of these 4 gigabit locations in the main memory, right, you can see the difference. And so this is why we have different addressing names for registers versus our main memory. Now, registers, and I'm not going to stop talking about it, they're not going to go away. These perform several different functions. Some registers are just scratch pads, right? And they just hold data elements or addresses of data elements or pointers, right? And they're just places where we stick data when we just need to put it somewhere for just a minute, right? Like a scratch pad. Some registers perform special functions, right? Some are loop counters that count the number of times that a loop has iterated. Some record the current states of the processor so that we can access and we know what's going on with the processor state. And then probably the most important register in the CPU is its program counter, which you can see here on the figure is named PC. And this contains the addresses of the next instruction to be executed. So remember, instructions happen in a sequential way, right? They're all queued up in there to happen in the order that they were received. And so once the CPU is done with the current instruction, the PC, which is also sometimes called the instruction pointer, don't get confused, those are the same thing, tells the CPU what it's going to do next. So let's talk about architecture here for a second, because I really feel like we get hung up on the terminology. And so computer architecture is the same world in the world of building, right? Like if we're physically building something and you call up an architect, they're going to talk about the structure, right? Design and planning. And computer architecture really just describes the structure of a computer from the perspective of the programmer or the compiler, whoever's writing that code, rather than the electronic engineer, right? And that's where I think a lot of people get tripped up. I don't assume that you've had any electronic engineering. We do talk a little bit about voltage and things just so that you understand how system clocks actually work and what actually makes those gates happen. But we don't get any deeper into the weeds of the actual electronics that an engineer would care about. We're software developers. And so computer architecture from this standpoint is really just there to help us understand how we need to write our programs and how our code is being interpreted and what is actually happening inside of the computer. So don't get too tripped up in the idea of architecture. We're not actually talking about building a computer at all. All right, so instruction formats. How does this actually work inside of the CPU? And computer instructions can have many different formats. But for the sake of simplicity, we're going to assume that the computer that we're working with, our generic computer, provides instruction in 3 different formats, right? We're going to have, and I'll show you an example here on the screen. We've got our LDR. Let me get my pen out here. Right, so our LDR, which is our register, our destination, right, and then our memory source. We have our STR, which is our register source and our memory destination. And then we have our operation, which has our register destination, our register source 1, and our register source 2. So when we write instructions, this is our syntax. This is our format that we're going to use. And we can see some examples down here. So first off, we're like, what are these letters? What are these acronyms? What are these? So let's talk about this for a second. So they're not exactly abbreviations. They are kind of shorthand for the types of instructions that we want to perform. So LDR, we can think of that as a load instruction. So it takes in our memory source and register destination of loading something from that memory. STR, which is a store operation, allows us to take our register as a source and put that in memory somewhere to store that. And then, of course, our operation is something that we want to do where we have our sources of information, right? We can kind of think of these as our arguments, and then we have a destination. Whatever operation we perform on these arguments, this destination is going to hold that result for us. So looking at these examples down here, let's take a look at what these instructions are saying that they're doing. So we're loading our R1 register with the value 1, 2, 3, 4. We're storing something into our memory destination. So we're storing this value from R3 into this destination. If we are performing an operation, you might see it like this, add. That's a pretty easy idea of what we're doing. We're taking a value from register 2 and a value from register 3, adding them together and putting that result into register 1. And sub, right, which you might already realize is subtraction, does the exact same thing, but does the subtraction, right? So when we are writing these kinds of instructions, this is essentially what we're doing. So our stored program machine, right, is a computer that has our program in its digital form, in its main memory. That program counter points to the next instruction to be executed, and then it's incremented after each instruction has been executed. The program and data are stored in the same memory. We can think of this in a very simplistic way, but in reality, today's computers, like the one that you are watching this lecture on right now, operates in a two-phase mode called fetch execute. So if we went back to computers that were sequential, where everything was just in a queue, that work at this very simplistic way, they were slow, right? And so we have developed different methods of fetching those instructions and reading from memory and decoding so that it's all kind of happening at the same time, so that our execute phase is executed by the CPU's logic. Everything's pipelined, it all overlaps, and so it happens much faster. And so it's, of course, harder to think about it like that, where we have this processor that's not just capable of doing one thing at a time. It's an extreme multitasking type operation, but that is how modern computers work in order to operate at the speeds that we require. So let's look at some additional types of registers and talk about some of the specifics of what these do. We've already talked about a couple of these, but the MAR, M-A-R, right? This is our memory address register. It stores the address of the location in main memory that's currently being accessed by a read or write operation. And this helps the CPU understand, like, where am I getting the information from that I'm using right now for this read or write operation. The MBR, or memory buffer register, stores data that has just been read from the main memory. We can kind of think of this as like a little cache, right? It's data that's either going to be immediately written to main memory or it's just been read. And usually we want that data readily available. Remember, registers are fast. And so we have this little area in the register where we can store that kind of information. So when we want to pick it back out real fast, it's right there. We talked about the PC, or the program counter, that contains the address of the next instruction to be executed. And then the IR, or the instruction register, stores the instruction most recently read from main memory. This is what the CPU is doing right now. Whatever's in the IR is what we're doing right now. What's in the PC is what we are going to do next. What's in the MBR is data that we are reading or writing right now. And what's in the MAR is the place where we're getting that information, the actual address. Then we have those registers that we've looked at that we can actually access, right? The R0 through how many ever general purpose registers. And these store our temporary or working data, results of calculations, places where we just want to store things that we know that we're going to need right away. All right. The simple computer that we're working with has 8, right? 0 through 7. We know that most computers have many more than that, but we're trying to keep it simple so that we can think about this in a way that is approachable. So once again, we're talking about ARM processor architecture to introduce assembly language and a modern instruction set. But remember, we're keeping our computer simple. The diagrams and the way that this computer is presented is much more simplistic than anything you've ever used in your entire life. I would imagine that most children's toys don't even, well, I guess that's not a good comparison. They don't really have CPUs. I probably had a some kind of Computron type computer when I was a child in the 80s that maybe worked something like this. These are extremely simplistic. So take it a little bit with a grain of salt, but it does help you as the beginner to approach how computers actually work and what that is like. So we're going to start here with our hypothetical stored program machine, and we're going to walk through this diagram so that we can see all of the different areas and how all of this works, right? So we're just going to, it's almost like a flow chart. We can just walk right through it. So starting with this section up here that's highlighted in red, we can see we have our memory address register, we have our program counter, here's our main memory, right? Here's our memory buffer. Here are all of our buses, right? Moving data around. We have our incrementer so that we know how many times we've done this. We have some opcodes, some operands, right? What are we doing? What's our instruction? What are we doing it on? All right, so the program counter, right, our PC, supplies an address to the memory address register, which holds on to it while the instruction is looked up in memory. So if we wanted to take a pretty simplistic view of this, right, we could think about like maybe a physical address. So you're like, I want to go to the bank. I know the bank is on 123 Main Street. So our memory or our program counter says, I want to go to the bank, and 123 Main Street is where I'm going. And so the memory address register says, okay, 123 Main Street, let me look that up. Kind of like Google Maps, right? So we go out to the map, we look up, okay, well, where is it? How do I get there? What's my route? And then we can get in our car and we can go to the bank. We know how to get there, right? We can load that instruction into the memory buffer. So the memory buffer, right, that MBR, contains the copied instruction register where that opcode is decoded. So what do we want to do? We want to make a deposit, right? So if we want to make a deposit at the bank, that's our opcode, right? We're depositing money. Operands would be how much money? Well, let's say I have $100 I want to deposit into my bank. So my opcode is deposit, my operand is 100. My memory buffer register is holding that instruction that's been loaded in, and then it's copied to the instruction register so that I know that it's happening. So let's walk down to the instruction register. So this is our execute phase. So we see here we're now in this yellow section. So we're at the bank. We've told the teller we want to make a deposit of $100. And so in this execute phase, the operands are read from the register file. So we put that the memory buffer register, put that into the register of what it is that we want to do and how much of it we want to do, right? Our operands. And then our arithmetic and logic unit, the ALU, is where they're operated on. So this ALU, in our analogy, we can think of this is the teller, right? So this is, or maybe even the computer, computers and computers, that the teller is using, but takes from that register file, right? Takes that money from us and then puts that into our account, right? Assigns our account number a new balance of $100, processes that, gives us our receipt, right? And then once they're operated on, right? So if we had $500 in our bank account, we deposit 100. Now we have 600. So we've added, right? Essentially, we've done a sum operation or an add. And then the result is passed to the destination register. So remember our three operand instruction set, like doing an add, said, take our register where we want to put the result, let's say R3, and if we have two items that we're adding together, so R0 would be my $100, and R2 R1 would be the balance of my account, my $500, and then I want to add those together and put those into the destination register. So now I have all three of those values stored in memory. I've performed my operation. If the operation requires memory access, so in this case, I would say, yeah, I mean, I had to access memory because I had to go get the current balance of my bank account. The memory address in the instruction register is sent to the memory address register, and then a read or write operation is performed. So once all of this down here is done, we come back through the bus, and we come back to the memory address register, and we, in this case, would write the new balance to memory. So now this computer would know I went to the bank, I went to the address that I said I wanted to go to, I performed the operation I wanted to do, I updated a value, and now I can write that to memory and we're done. And so that might seem like I don't know, that's a heavy-handed kind of analogy, but it's a little more accessible since it's probably something we've all done. But it's not like it's that far out of the line for what actually happens in our hypothetical stored program machine, right? Walking through this type of scenario. So let's look at instructions, right? How does this actually look when we write instructions? So here's that fetch execute cycle. Okay, so starting with fetch, right? We can probably all guess what fetch means. Fetch means we're going to get or do something. So from our PC to our MAR, our program counter, which contains the address of the next instruction to be executed, is copied to the memory address register. So that's where it is going to be used to access the memory that we want to read the instruction from. Then we increment our PC, our program counter. So the constant 4 is added to the contents of the program counter. So we know that it's time to execute the next instruction. And remember, in this scenario, instructions are executed sequentially unless we have what's called a flow control instruction, which modifies the natural sequence. And in this case, because we're talking about ARM, the increment is by 4 and not by 1 because ARM's instructions are each 4 bytes long. Our next step, and you can see the comments out here anytime we want to write a comment, it's prefaced by a semicolon. We take the contents of the memory location pointed to by the contents of the MAR, and it's copied to the memory buffer register, which is the MBR. Since the MAR contains the address of the next instruction to be executed, the MBR will now hold the opcode of the current instruction, right? So the MAR denotes the contents of the memory location whose address is contained in the MAR. I know that sounds weird to think about, but that's what's happening. All right, then finally, the contents of the memory buffer register are copied to the instruction register. So the instruction register now contains the instruction to be executed. The instruction bits are used by the control unit to generate all of the signals that implement the instruction. And so we didn't talk too much about the control unit, which sits over here, right? So let's hop back for a second and make sure that we didn't neglect our control unit. The control unit interprets the instruction from the IR. So it causes the instruction specified by the opcode of that instruction to be executed. So if our opcode is add, it literally uses a stream of clock pulses and that opcode to generate all of the signals that control the computer's buses, memory, register, functional units, right? We talked a little bit in chapter 2 about all the gates and register clocks and how we move data around the computer. The control unit is what makes that happen. So the control unit knows that to do an add, this is my sequence and pattern of signals to all of the gates that I need to use. Here are all the values that I'm using, right? I got that data from the IR. And then when I'm done, I have my result. So we don't want to neglect the control unit because it is actually what's driving these processes. And if you want to walk through this example that I just walked through with all of the instructions, this is that, but in a visual form. So real quick, we can take a look. Step one, how do we move the data? We can take a look at how the arrows move, taking our MAR into our MBR, taking our MBR into our IR, and then our address into the MAR, right? We're just moving stuff around. That's all we're doing. We're just moving stuff around. So this is how we can do this in a visual way. So you can take a look at these figures if that helps you think about those instructions a little more visually. I know some of us are more visual. Hopefully that helps you kind of see how this works. So here's a fun problem. Let's talk about constants for a second. We've demonstrated in the previous example how a computer can access data from memory using an operation like LDR, register 1, 1, 2, 3, 4. In that example, 1, 2, 3, 4 refers to the contents of a memory location that we're just calling 1, 2, 3, 4. But suppose we want to load the number 1, 2, 3, 4, like literally itself, in this case into register 1. We call these literal operands, right? So it's not a memory address, a literal value that is just used directly in an operation. Like in our previous example where we incremented by 4, that's also a literal operand, as opposed to the contents of a memory location. And so we do this in our code by prefixing it with a hash symbol, right? So we can see here, for example, we have add register 0 is where our data will go. The value of register 1 and the literal value of 25. So in our case, in our example with the bank, right, we would say add R0 if that's where we want to put our sum, R1 if that holds my current bank balance, and pound sign, hash sign, 100 as the literal value that I want to put into this operation. So it would take the contents of R1, which we said was $500, literally $100, add them together. Now I have $600 and it puts that into R0. And so we have to make sure that we are doing this correctly. When we start to look at our assembly code, we put that pound sign in front of our literal values. But that's always a good thing to think about, right? How do we actually do this? So we've looked at some instructions, but let's talk a little further before we continue. Some simple instructions that can be used in our examples. These are ARM-like instructions in the sense that they use the ARM assembly language format. But ARM does not fully support load and store instructions with what we call direct or absolute memory addresses. So you may see some examples of that if you actually go out and look at some other assembly code, that it does actually matter a little bit syntactically how it's written for the type of platform that you're writing it on. So I know a lot of people just think assembly is assembly, but it does actually matter the platform that you're writing it for, which is just one of those other things that programmers have to live with. So let's look at our examples. So LDR, register 0, and an address is going to load the contents of whatever memory location at that address is into register 0. STR is a store operation, so we're storing the contents of register 0 at that specified address in memory, so kind of the opposite type situation. Add, right, adds the contents of registers 1 and 2 and puts the result into register 0. Same thing with subtract register 1. Actually, it's register 2 from register 1 into register 0, so you have to read it that way, which makes a difference when you're subtracting. BPL and then a target. BPL, it basically says if the result of the previous operation was a positive value, then we're going to branch. And so it's like an if statement. So it looks at that target, which in this case, like maybe we did an add into R0. And if we want to know if that's a positive, then we're going to branch to an instruction. But if that's a negative, we want to branch to a different instruction. So BPL branches to a positive. BEQ, if the result of the previous operation was 0, branch to an instruction. And then B, just B for branch, just lets you jump to an instruction stored at the memory address target. So whatever instruction is at that target, we're going to jump there. Now I want to stop here for a second because this is where a lot of what we call arbitrary code execution takes place. So arbitrary code execution is a process by which instructions get called and they aren't necessarily the code that or the instruction that should have happened, right? So, and it's a great concept in computer security where you have an attacker and they have an ability to run commands or code on the attacker's machine and execute instructions for a target process. And it really all comes down to the fact that you can pick out in memory the fact that you have an instruction stored there and then just do that instruction without going through the logical branching sequence of values that would usually get you there. And so if you've ever heard that term before or you have thought about that process before, this is essentially how that happens. It's because there is an instruction code that just lets us go to a target and perform that operation. So the last little bit here that I want to talk about before we wrap up our chapter 3 part 1 is about flow control. So flow control refers to an action that modifies our instruction by instruction sequence of a program. Right? And in programming, we kind of talk a lot about flow control. We learn about conditional behavior, if statements, switch cases, while loops, things like that allow us to change and branch inside of our application code. Well, this is the exact same idea, but it's happening at this memory instruction level for our machine. And so let's take a look at this figure while we talk about flow control. So this figure here shows the information paths that a computer has and is required to implement for conditional behavior. And a conditional instruction, which we saw in our instruction set sample like BEQ, results in either continuing program execution normally with the next instruction, whatever that may be in the sequence, or loading the program counter with a new value and then executing a branch to another region of code. And so when we do that, right, let's actually walk through an example that might help. So here is that same diagram, but with our path outlined for kind of our feedback from an ALU to instruction. So when we start with our program counter that fetches a conditional branch instruction from the address in memory, that branch instruction reads the contents of the condition code register, whose bits are determined by the result of previous instruction. So when executed, the conditional branch instruction performs one of the following two actions. So if the bit in the CCR being tested is false, the processor fetches just the next instruction, right? We increment by 4 because we said 4 bytes. But if the bit in the CCR being tested is true, then the program counter is loaded with a new address from the operand field of the instruction register, and a jump is made to this new address. So as we move around in this scenario here, right? We can see how we can basically take what we're doing, like in this sequential way, and then based on a value, just do something else, which is essentially what we do in software development when we write code that contains conditional values. So the next question, hopefully in your mind, is how does it know? How does it know? What's the status? And we call these status bits, or sometimes we call these flags. But ultimately, this is how conditional branches are implemented. When the computer performs an operation, it stores a status and a condition in that information into the CCR. And so the processor records whether the result is a 0, let's say a Z, which is a negative in 2's complement terms, right? Or so we might use an N for negative. Or if it generated a carry, which would be a C, or if we did an arithmetic overflow, because remember, we also need to know if that happened, which we would use a V. So if we had all of this information in our CCR, then we could kind of look at each one of those status flags, because the CCR bits are updated after each operation. And then, well, that's being a little economical with the truth. The actual situation is much more complex, but let's stick with simple. After that information is updated, we can then look at that status flag and then decide what we want to do next. And looking at this example, we have to remember the computer is doing the arithmetic in binary, which is why we talked about this in the previous chapter. We have to understand that this is what's taking place. So let's look at an example, right? An example of a conditional operation. So let's take a look at this instruction set right here. And we'll demonstrate how to use the conditional branch operation, the BEQ, to implement kind of this high-level language construct. First, recall that the opcode field of the BEQ instruction in the IR selects a bit in the CCR to be tested. So the Z or the N or the C. If the tested bit is 1, then the PC is loaded with a new value, such as the branch target address. Otherwise, the PC is not modified. So we can see here that we're going to subtract 1 from the whatever value is in register 5, and we're putting that back into register 5, totally legal. Then we can see our branch operation on 0. So if this result is 0, then we're going to go to a line in our code labeled on 0. And so we can see that there are 2 operations in our code, not 0 and on 0. On 0, we're subtracting R2 from R3 and putting that into R1. If it's not 0, we're doing the same thing, but we're adding. So this is exactly like the kind of decision-making logic that you would take place in any other programming language that you've learned, right? So we do the subs operation, as noted with the sub, with the S means we're updating that flag. And then our BEQ on 0 forces a branch to the line labeled on 0 if the outcome of the last operation was 0. Notice that nowhere in here did we have to ask, because BEQ asks for us. And I know that that's tricky for programmers because we're so used to, like, if this value equals something or is greater than something, or we're actually forming a logical condition. But in this case, it's going to go check that flag for us and tell us yes or no. So let's look at the code. This is essentially what we want to do, right? If we pseudocoded out this problem, this is what we want to do. This is not assembly. This is pseudocode right here, this right here. So q minus p equals x. If x is greater than or equal to 0, then we're going to do our add operation. And then this, if it's not, then we're going to do our add operation and add p to 5. If it's not, then we're going to take our p and add it to 20, right? So we're just pseudocoding. Translating that into ARM code using the subset of ARM instructions that we defined in the earlier panel. Here's how this goes. Now let's look at this section down here at the bottom, the DCD. The DCD directive reserves memory locations for the 3 operands, which is kind of like defining variables. So P DCD 12, we can see from our comment section here, these 3 lines reserve memory space for the 3 operands, P, Q, and X. The memory locations are 36, 40, and 44 respectively. We put values into them, so P DCD 12 means that variable P is going to hold the value of 12, right? Just like we're defining variables. There's not really anything groundbreaking here. But we can walk through this instruction of our pseudo-coded problem. So loading in to R0 the contents of location P, right? Which wherever P is at, we know that's 12. Then loading into R1 the contents of location Q, which we can see has a value of 9. And then subtract with the S, so we're modifying the flag, R0 and R1 into R2, so subtracting the contents of Q from P. Then we test. So BPL then, this is just like it's a name, it's like a variable. We're just saying go to the then line, just like in the previous example where we used on 0 and not 0, right? So we're just saying then, if that value of X, which is in R2, is greater than or equal to 0, then we'll execute the then part. But if it's not, then we're just going to come down here to the add part. So this was our else, and you notice it's kind of written the opposite direction. So we're saying if this is true, then do this. But if it's false in our else, we'll just continue. So if it's false, then we're going to add 20. So taking R0, adding a literal 20, putting that into 0, and then making sure that we skip past the then by using a branch to the exit, because otherwise we would fall right into this step and we would do this step. If this was false, we hop down here to the then and we add a literal 5 instead. We're going to, down here and exit, either way, we either come to the exit or we drop to the exit. We're going to take that memory location of X and make sure that's stored in register 0, and then we stop. That's the end of our program. So we can see here, this is where the branching took place. This is where the test is. In that BPL then. And then this step right here, this is an unconditional branch. So we want to make sure that we don't fall in to an instruction that we don't want when we're doing branches like this. Then if we also wanted to look at this in that RTL, that register transfer language notation, this is the same sequence of instructions written in RTL. Now RTL, it's kind of like pseudocode as well. A lot of programmers, they learn to pseudocode and then they learn to actually code. Remember I talked about how there's some differences in assembly instruction depending on which actual microprocessor platform architecture you're working on. With RTL notation, this is kind of like pseudocode for assembly. We can talk about register movements and kind of a high-level method of describing the architecture of a circuit without having to actually write code that we then have to worry about syntax. So this is the exact same problem written in RTL notation. So this is the end of Chapter 3, Part 1. We will continue in our next section by talking about components of an ISA and really digging into some of the things that we need to understand about the human and the compiler before we look at a real microprocessor in detail.